3.3 example 3, as promised, is factoring a quartic, which is a little trickier because, you know, cubics can have as many as 3 factors, quartics can have as many as 4 factors, and basically the degree of the polynomial corresponds with the maximum number of factors. So we're going to start this off the exact same way. We want to use our remainder theorem. I'll write it again, that x minus a is a factor if and only if, I'll use the 2 f's in this case, x minus a is a factor if and only if, p of a is equal to 0. But what's a? And so I'm just going to put the candidates for a, well, I'm not going to put quotations, are factors of the constant, I'll just sneak in term underneath there. So for this particular polynomial, the constant term is 24. I know it's negative 24, but you don't need to worry about that negative because we're going to check the positive and negative of each factor anyway. So I am going to put the number 24 here. And then what we could do is check positive 1 and negative 1. Let me use the dot instead of the x there. So 1 times 24 is 24. 2 times 12 is 24. 3 times 8 is 24. 4 times 6 is 24. And those are our factors. So realistically, because we check the positive and negative, we could be checking 16 things, which is a lot. So there is a workaround to this, which is using your graphing calculator. Quite frankly, you could use your graphing calculator and find the x-intercepts, and those are factors. But I want to show you how to do it with the kind of heart and spirit still in this 3.3 lesson. So you need your calculator, obviously, and I'm going to put the function in for y1. And I've pushed this a few times in class when we were in class, that it's a really big advantage that once you have a function in, if you want to see that function at different points, don't use your graph because it's going to draw it, it's going to take a while. And if it's out of the window settings, you have to change the window settings. So instead, I'm going to go to second window, which takes me to the table setup. And I just want to make sure your independent is on ask. Because now when I go to my table, I have a bunch of different values in here. And what I'm going to do now is I'm going to put in the factors of 24. So there's positive 1, negative 1, positive 2, negative 2, positive 3, negative 3, positive 8. Let's do 4 there, sorry. So 4 and negative 4. And then I'll just put in the 6 and negative 6. And then we could keep going, right? Like we're missing, this is, you know, just a little bit over half of the potential answers. And you can start to see how some of these don't work immediately, right? P of 6 is 384. Well, that's not 0. So x minus 6 isn't a factor. P of 4 is 24. Again, not 0. So x minus 4 is not a factor. But look at 2, negative 2, and 3. We actually found out, and this is certainly not by design, that we got 3 of our factors. Now I'm going to put those on the page. So that's 2, negative 2, and 3. So we found that P of 2 is equal to 0, P of negative 2 is equal to 0, and P of 3 is equal to 0. And I'm just going to put from our table there. The one thing I would really not recommend is trying to find all the factors and then just assuming that you have everything correct, because if there is some kind of a vertical stretch, you still might not have actually found the specific polynomial you're looking at. Now, for this particular question, that won't be the case, but I really want to show the factor technique again. What I'm going to say then is that because P of 2 is equal to 0, x minus 2 is the factor. Now, I do want to explain it, at least like I did in the previous example. Again, assuming that this is P of x, because it's the only thing we're talking about, I could say that P of x then is equal to some quotient function times the x minus 2. Now, I'd like to point out that we still know that P of negative 2 is equal to 0. Now, what's really important is if I look at putting negative 2 in for x in the statement I just made, I am not going to get that, x minus 2 isn't 0. Now, what this means then is that if P of negative 2 is 0, I can also say that Q at negative 2 is 0. Now, all that really means is that if you found the factor of the large polynomial, once you do some long division, if you knew that something was a factor before, it is still a factor. You just got to be careful using that factor twice, because that's only going to be usable if you have something called multiplicity, which we look at in 3.4. So what I'm going to do is I'm going to use this table and I'm going to figure out Q of x. So I'll just write underneath it that Q of x is equal to P of x divided by x minus 2. This I'm going to do synthetic for. All right, again, just trying to show you the different techniques. So to set up synthetic, I'm going to put that kind of L. I'm going to put the value of x that makes my factor 0, which is positive 2, because we're dividing by x minus 2. And then I'm going to put the coefficients of my quartic, which are 1, negative 5, positive 2, positive 20, and negative 24. Be careful doing questions in the textbook. Sometimes they won't have that in descending order, and you need to put it into descending order. All right, so doing our synthetic, the first number automatically drags down. We multiply by positive 2. Then we add downwards. Let me put that multiplied by 2 there. Negative 5 plus 2 is negative 3. I multiply by 2. That gives me negative 6. I add downwards. I get negative 4, which means I have negative 12, which gives me positive 8, which gives me, oh, what did I do there? I made a mistake somewhere. Oh, that's not negative 12, is it? Some good multiplication there. Negative 4 times 2 is negative 8, and it adds to positive 12, which then gives me positive 24, which adds to 0. So I'm adding downwards throughout this chart. Now, what I've gotten away with here is I now know what q of x is. So I'm going to write q of x is equal to, for this particular question, it's going to be 1x cubed minus 3x squared minus 4x plus 12. Now I can say then that p of x, the overall quartic polynomial, is what I just found. X cubed minus 3x squared minus 4x plus 12 multiplied by the divisor, which was x minus 2. And it's important that what we've done now is we've represented the quartic polynomial as a cubic times a degree 1. And basically, we rinse and repeat. And I want to re-emphasize that I know, I'm going to use a different one here, that p of 3 was equal to 0. We determined that from the calculator. Well, that means that that cubic, x cubed minus 3x squared minus 4x plus 12, is divisible by x minus 3. So I'm going to do that. I'm going to take that cubic, 1, negative 3, negative 4, and positive 12, and I'm dividing it by x minus 3, so I'm going to positive 3 there. The 1 drags down. I multiply. I add that down, I get 0. Nothing wrong with that. That means that this is 0, so negative 4, so negative 12, so 0. Now, all I've done here is I have made the statement now that x cubed minus 3x squared minus 4x plus 12 is equal to, when I divide by x minus 3, it's x minus 3 times x squared plus 0x minus 4. Now, you don't need to put 0x there, but I want to make sure we see that connection with the synthetic. And we are going to make one more kind of overall statement, and we're almost done. These questions are definitely a little wordy. That means that the overall polynomial p of x can be written as that quadratic, x squared minus 4, times what we divided q of x by, that's x minus 3, times what we divided p of x by, which is x minus 2. And again, now we see that the quartic can be written as a quadratic, x squared minus 4, times 2 degree 1s. And so we go one step further. To factor x squared minus 4, we use our quadratic techniques. That's a difference of squares. So that's going to be x minus 2 times x plus 2. The x minus 3 is still there. The x minus 2 is still there. And then what we can do is, because there's two factors that are the same, we can write it as that factor squared. And that's going to be something, oops, that should be a 2 there. That's going to be for something very useful in 3.4 when we look at talking about multiplicities of functions and so on. Now, I'd like to reiterate one last time that if you're not sure you've done this correctly, I just need to steal this polynomial piece. I think it will move. Okay, good. If I want to see if I've done this correctly, as tedious as it is, what I could do is I could check the expansion. I am saying that this quartic is factorable into those four factors together, because 1 squared. We could check that. We could see if that's true. So x minus 2 squared is x squared minus 4x plus 4. X plus 2 times x minus 3 is x squared minus 1x minus 6. And if I multiply those together, and this gets a little tricky because it's a trinomial times a trinomial, but I'm going to multiply the x squared onto all three. That gives me x to the power of 4 minus 1x cubed minus 6x squared. Then I would have negative 4x cubed, positive 4x squared, positive 24x. I ran out of room here, but I'm going to try to sneak it in. I'd have positive 4x squared, negative 4x, negative 24. Now when I collect my like terms, I have x to the power of 4 minus 5x cubed. I'm just going to cross them off as I go so I don't miss any. The x squareds, I have negative 6 plus 4 plus 4. So that's going to be positive 2x squared. That's this guy, and this guy. 24x minus 4x is positive 20x. And finally, the constant term sneaks in there. And I really think it's important to recognize that we have not changed the function. We've changed the appearance. And if I asked you, what makes this equal to 0, it is far better to have the factored form. Because if I knew that that factored form was equal to 0, then it's either x is equal to 2, x is equal to -2, or x is equal to +3. So factored form is far superior than general form. It gives us more information about the actual polynomial itself. And after 3.4, it also tells us about the behavior of the polynomial near those x-intercepts.